Welcome back. Today we will going to start a new set of lectures on particularly mathematical properties of fundamental equations. In the first 2 weeks we looked into the fundamental thermodynamic equations and its basic derivations and the concept behind that, and subsequently we looked into the equivalent properties, the driving force for variety of different changes in the thermodynamic properties, and then we spent some time to revise first law and second law. So, with that background, now we can start a little bit more mathematical aspects of thermodynamics. So, this lecture will specifically focus on mathematical properties of fundamental equation. Okay. Now, we will start with the Euler equation. Okay. So, we will look into the thermodynamic function or the potential, which is usually a function of S, V and some other variables. So, we are considering all these variables are extensive. Now, the Euler equation or theorem says that if you are going to consider a different size of the system such that the entropy is multiplied by lambda and the volume corresponding is also multiplied by lambda. So, that is a enhancement in the system size, and similarly for other properties, then this must be equal to lambda u S V x 1 and x t. So, this comes directly from the extensive properties of this thermodynamic potentials, which are extensive in nature. So, where x could be, because it is an extensive property, x could be something such as moles of the component. So, we can consider something like this, where we have u lambda s lambda v, and instead of x I can put number of moles. Okay. And in that case this will be lambda u s v okay. Now, if you take a partial derivative with respect to lambda on each side, in that case I can get this lambda or del u by del lambda s times del lambda s by del lambda. So, that is the first variable, plus del u by del lambda v times del lambda v by del lambda, and then we can have the partial derivative with respect to lambdas of moles, and then this can be brought under some summation. So, I can write it as del u by del lambda n I times del lambda n I del lambda. Okay. And this would be simply del lambda u by del lambda, which is nothing but u. Okay. So, right hand side is u. What about the left hand side? So, this by definition this would be simply the, if you look at the partial derivation of del u by entropy, this must be S, this must be S, okay, and this would be minus P, and this would be your V, this would be your mu I, and this would be N I. Okay. So, in that case, so what you have now is your u, okay, this is equal to, this is right hand side. So, I brought it here, this is equal to T s minus P v plus summation mu I N I. Okay. So, this is the standard Euler relation. So, we started with the property of the extensivity of the thermodynamic functions. From there we can obtain Euler equation. Okay. Now, you can do the similar exercise not just considering the internal energy, but if you consider this as an entropy, also entropy as a function of U, S, V and so forth, then essentially you should be able to obtain a different expression for Euler, which would be your something like this. So, if you consider in the or based on the entropy relation representation, that is S is equal to S of U, V and so forth. The S, the corresponding Euler relation would be, you will do the similar exercise as we have done for the U, and you would now obtain an expression of S in the same sense or in the same line as we did for internal energy, and I will write it directly without deriving it. So, you can obtain this as a Euler relation based on that. Now, if you rearrange this expression, what you are going to get is T s is equal to U plus P v minus summation mu I n I, or U as T s minus P v plus summation mu I n I, which is same as that. Okay. So, this is exactly the same as the other expression. Okay. Now, if you take this relation, okay, so now we can take the derivative of this expression. Okay, let me just so we do differentiation or differentiate the above expression. We get du is equal to T ds minus S dt, okay, and from here minus Pv is minus P dV minus V dP, and then you have this plus summation mu I d n I plus n I d mu I. Okay. Now, earlier we know the fundamental expression of internal energy in a differential form is du is T ds minus P dV plus summation mu I d n I. Okay. So, this we know. Okay. So, if you use this expression, so this is, let us say 1, this is 2. So, using 1 and 2, I am going to get this. If you just subtract this, then I can get a 0. So, that means 0. So, it is like the following 2 minus 1 S dt minus V dP plus summation n I d n I. So, this must be equal to 0. Okay. Okay. So, what we did here is that we differentiate this expression, and we obtain du is equal to T ds plus S dt minus P dV plus V dP, and this mu dn and n I du. And we know from our fundamental relation expressions that the differential internal energy is written in this form. Okay, T ds minus P dV plus summation mu I d n I. So, if you subtract this 2 with minus 1, what we are going to get is S dt minus V dP plus summation n I d mu I. Okay. So, now this expression is puts a constraint on the intensity variable. If you can clearly see this, it says that the differential amount of T is connected to the other variables. So, it gives you a relation of constraints of the internal of this intensity variable among the intensity variables. So, essentially it gives a relation between Tp and mu I. So, this expression is called Gibbs-Duhem equation. Okay. Now, let us consider for a single component. So, if it is for a single component, okay, we have S dt minus V dP plus n d mu. So, this is for single system. Okay. Now, as I said, this gives you a relation or constraints between T, P and mu. Okay. So, if you rearrange this expression and bring your d mu here on the other side, you can get this relation of V by N dP minus S by N dN. So, we can now write in terms of molar values. So, I can write in this way as well. Okay. So, I can write in this way, or you can also say it as V bar and S bar. So, this is another symbol which we often use. Now, this is for the case of expression based on the internal energy, right. Now, I can use the similar kind of exercise, or I can do the similar exercises based on entropy. Okay. So, if you start, or let us try to do this. So, let us say this is based on entropy relation. If we try to come up with an expression, then I will start with the S here. This I will rewrite again in this way. So, S is U by T plus P by T V minus 1 by T summation mu I and I. So, this is the Euler expression for based on the entropy. Now, you do the similar exercise as we have done for the internal energy. So, we are going to do take a differentiation on the both side. Okay, and let us do this. ds is equal to u d1 by t plus 1 by t du plus p by t dv plus v db by t. So, now the third term is 1 by t. I can bring t inside, okay, and I can do the following summation mu I d n I by t plus n I by t d mu I. Okay. So, this is the expression for this if you take the entropy based. Okay, and now the expression for mu, or sorry, expression for entropy, we know that ds is du 1 by t plus p by t dv minus summation mu I by t d n I. So, this is the expression for ds. You can clearly see from our first law expression also, or this expression for du which we know. So, if you take out the t here, you are going to obtain the same expression here. So, this is equation, let us say 3 and this is 4. Now, using this 3 and 4, this is the expression which it comes, okay, and this is the expression which would be your Euler relation based on that. Now, if you consider for a single component, for a single component, this would be your u d 1 by t plus v dp by t. So, there should be a negative sign here, minus n d mu by t. Okay. So, we have this now expression. We can divide this this expression by n. In that case, you are going to get a small u d 1 by n plus small v, the smaller volume, and this would be your d mu by t. Okay. So, this is the expression which we are going to get based on the entropy. Okay. Now, what I am going to do is I am going to apply a bit of what I am going to consider is a simple case and try to extend this understanding. So, earlier again let us summarize this. So, the purpose of this exercise is to demonstrate an expression which connects between the intensive variable. So, it gives you the constraint between the intensive variable, okay. And the earlier expression which we made use of it here, okay. Later on we use this Euler expressions, okay, which was based on the extensivity of the variable, and later and obtain the expression of the Gibbs-Duhem relations. So, the Gibbs-Duhem relation basically is nothing which provides the constraints on the intensive variables. You can come up with a internal energy based expression, or you can come up with a entropy based expression. That is why we did this both the exercises, and clearly you see this relations are different. So, this is the one which is entropy based, and this is the one which is internal energy based. Both provides both gives you the constraints between the intensive variable, okay. So, taking this forward, now let us consider an ideal gas. So, consider a simple ideal gas or monatomic in some sense, okay. Now, this is characterized by two equations. One is, of course, we know the equation of state, which is P v is equal to nRT, and the other is that internal energy is proportional to nRT, and the constant is C, the proportionality constant, which is 3/2 for monoatomic. Okay. So, remember that this is for high temperature and low pressure, right. So, that is the definition which, or rather the validity of the ideal gas, high temperature and low pressure. Now, the question which we are interested in is to determine the fundamental equation. Okay. Where in this case, the u is explicitly expressed, so u expression is given. So, we need to use this expression to obtain the fundamental equations. So, let us try to do this exercise. So, we will rewrite this expression. So, rewriting the equation in the corresponding appropriate form. So, what would be appropriate form? We will write 1 by T as C r and u, okay, which could be written as C r small u, and the other one is, so this is the thermal expression, thermal equation of state. This can be written as P by T r by V, this is nothing but r by small v, okay. Now, these are the expression which comes directly from here. So, we are going to use a certain relation which brings this intensive variable or connects this intensive variable. So, let us look at a Gibbs-Duhem relation to start with. So, we will take a Gibbs-Duhem relation here. So, Gibbs-Duhem relation says the following, that d mu by T is equal to, so that is what we written for based on the entropy. So, if you want the fundamental equation, and then here we can get the expression for the entropy. So, this is directly from the which came from the Gibbs-Duhem relation based on the entropy relation, and now I can integrate this mu by T minus mu some reference value, and if you integrate this, this is u d 1 by T is C r by small u plus V dP by T, which is nothing but d r by V, okay. So, if you extend this, you are going to get this expression right hand side as minus C r ln some u minus divided by reference u minus r n V by V 0, okay. So, this is the expression which you can get from this. Okay, so now if you substitute this expression in the Euler equation, so this is a Gibbs-Diamond equation, but the Euler equation of the entropy is S is equal to 1 by T U plus P by T V minus mu by T N. Okay. So, I can obtain a molar entropy expression, because if I divide this by small s, I am going to get small s as 1 by T U by N plus P by T V by N minus mu by T. Okay. So, now you can put this expression of 1 by T. If you see this expression, 1 by T is nothing but CR n by u or CR by small u. If you plug in here, you can show that this is nothing but C plus 1 by R minus mu by T. So, this is your small s. Okay. So, now you look at this expression. So, this is, let us say, this is your 5, this is your 6. Okay. Now, if you look at this expression and this expression, and because C is a constant, R is a constant, and if you consider S minus S0 some reference, then this is going to be mu 0 by T 0 minus mu by T, because this is going to be constant, and hence it is going to cancel out. And this essentially is nothing but, if you look at equation 5, this is nothing but CR ln U by U0 plus R ln V by V0. So, that is your basically the fundamental equation which comes for the ideal gas system, which we have just described for the simple one. Okay. So, this is what we have made use of. Two things we have made use of: the Gibbs-Diamond relation, that number one. The number two is we have made use of the Euler relations also. So, with that I will stop in today's lecture, and I will continue this exercise and bring more mathematical relations to obtain a variety of different ingenuity which normally we see in a thermodynamics course. So, we will build it upon what you have learned today, and in the next lecture we will take up something called generalized thermodynamic function. Okay, so, I will see you in the next lecture.